Recording is rolling. It is Friday, September 9th. We have ourselves a short day. Let's make the most of this. Right. So let's go through this. Let's start. Hopefully, some guys solve this donkey question over here, which I'll go over with you guys for a few minutes. But let's go over agenda. So your guys' college physics chapter 3 homework, I'm gonna pick up Monday. Remember, you guys have the solutions. They're posted on Classroom. They're also stapled on your desk, so you can check your work, see how you're doing. Some projectiles and 2D questions. Actually, one of them. Well, here. Okay. I just gave you guys a quiz. You guys see a quiz on your desk? Looks like this right here. Guys, this. Okay. So this is let's have this due on Tuesday. Okay. Actually, well, I got this up. So good, you got some pointers here. So the first question involves some graphs involving a cannon perched on the edge of a cliff. Now, if you do look back on your notes, I did give you, we did do graphs, like this set of graphs related to a similar situation, like a cannon blasting horizontal at the edge of a cliff. I think we also did one like this, like a cannon on the ground, like what does graphs look like? Right, so the one on your quiz is a modified version. You either have a cannon that's blasting from the edge of cliff down about 30 degrees or up about 30 degrees. You guys see one of those? I gave you guys a little picture in the top left. It's either down 30 degrees or up 30 degrees from the cliff. Okay, that? Right. So these graphs don't exactly match what's in your notes, but or maybe some of them do, but maybe not all of them, right? But I think you guys can use your imagination and figure out what would be different or what might be the same as what's in your notes, those scenarios that we did. Right? Question number 2. You guys see the question says that cannon fires cannonball. I think I gave everybody the same question on this one. You're trying to hit some target, some distance X away, some horizontal displacement away, and your task is to figure out how to angle the cannon. Right? Right. So do you guys remember yesterday I was taking you guys through the range equation and we got cut off the last 2 minutes of class. I did post a bonus video to Google Classroom if you want to see like the full version of this. Now the way I went with this was I went the optimization route, so there was this extra calculus step on tagged to the end. But if you rewind a bit and just go to this range formula, do you guys think if this is really solved in terms of variables? Can you do the algebra on this? So the way I derived this, I said, if you know the angle, you can know exactly how far it goes. Do you suppose you guys could do a little algebra switch on that and solve for theta given all the other variables? Okay. They didn't give you guys too many hits on that one, but I just want to show you guys that you're like really close to having that already solved for you in the notes. But I want you to know how to do that. Okay. There's a conceptual question down here, number 5. Everybody has a different conceptual question. There was a bonus page I gave you guys. You guys remember this page has all these projectile questions on the back that has a bunch of conceptual questions, right? I know we did a Kahoot once on linear conceptual questions. You guys did really good on that. I wanted to fit that into this class, but I don't think we'll have time. So here's what I do. I'm going to do the Kahoot conceptual questions with my honors kids. I will post that video as a bonus video to Google Classroom if you want to see what the answers to those are. But you guys usually do pretty good on those. Right. And then on the back side, there's 2 scenarios. There's these 3 questions and these 3 questions. And everybody has a little bit different scenario. They're all about equally as difficult. But if you pay real close attention, what you'll see is that this first scenario and these 3 questions, I give you guys some numbers and say like solve blah, blah, blah projectile scenario. And the second scenario actually is the first scenario, but it's just generalized in terms of variables. And I try to give you guys like nice numbers too. So the numbers all come out to like integer values and everything's like working really nice. So if you go through step by step, you can solve just with equations and numbers and then think, I wonder what big picture that would look like. You can piece together like solve in terms of variables, or maybe you're getting pretty good at this and you could just go straight solve from in terms of variables already. Because if you solve in terms of variables, this could solve any of these problems, and then you could actually just use that solution if you get the right ones. You just go plug, and just immediately get the answers to the numbers. Okay, you guys get that? Okay, all right, there you go. There's for how to navigate your quiz going on right there. Okay. Oh yeah, I really been wanting to get to this lab. We've just had this weird short talking week, but yeah. So we'll have to push up the lab to next week, probably Monday. I'm looking at. Remember how this is working. You guys gotta get this launcher. Actually, it has different settings. If you process once. Get here, one click, so you can keep pressing. Oh, actually, I think I pressed it all the way. Go to like 3 clicks, right? Then you can pull this. I think I demoed this yesterday. Ball goes, pew, goes flying. Right. So here's gonna be your guys' lab on Monday. I want you guys to tell me what's the blast speed from this cannon. Okay, like how fast is this launching? Right now, I'll leave it up to you how you design your experiment to do that, because I'm giving you guys a few days to think about it. How could I do that? Right. But you guys have cell phones with stopwatches. Do you think you could probably use some meter sticks? Do you think you could solve the whole thing with just that and the knowledge of what Earth gravity is? If you know what Earth gravity is, and you have some meter sticks and some stopwatches, do you think you can solve the whole thing? Maybe you could take a protractor if you want. There's a built-in protractor that thing too, right? Do you think you could possibly do a setup like this if we went out on the ledge out here by the stairs, right? On the balcony, right? Or if you like, do you think you could do a setup like this too, right? I mean, there's multiple ways you could solve this. I've had a group in the past do a third option that's not exactly either one of these. So there's another option you can do too. Don't want to spoil everything. How do you guys think about that? So we'll have to do that Monday. All right. Okay, so I think I covered all these things. All right, so any questions so far? So, right, so here's what we're doing rest of today. We're going to solve this problem of like pulling the donkey around. Right, and then we'll take the rest of class and I'll solve as many college physics chapter 3 problems as I can with you guys. Right, take you guys through as many of those. Okay. All right, so let's solve. 2 people pull a stubborn donkey. What is the net pulling force? Right, so I don't care about the friction that between the hooves and the ground that's holding this guy in place. I just care about what's the net force between these two. Okay, this guy has a rope that's pulling this way. This guy has a rope pulling this way. Something like that. Right. Okay. Now, there's a problem in the textbook that looks extremely similar to this, just has a little bit different numbers. Okay. But I tried to get like nice numbers here, where all the numbers are going to be integers, so you can crunch this and run and say, okay, yeah, I see the big picture of how this works. Okay. Now, before I start plugging and chugging and breaking out trigonometry and yada, right, let's look big picture about this. Okay. Because one way I told you could add vectors geometrically is tip to tail. You guys remember tip to tail? What if I take this 500 Newton vector and I connect it tip to tail with a 1,000 Newton vector? Wouldn't it go right here? Or you could do it the other way. You could take this one, line it tip to tail with the other one. Either way you do it, you see like a parallelogram forming, right? So, something like that. So do you think maybe the net force would be kind of forward, and then whether it's to the right a little bit or to the left a little bit, that's kind of hard to tell, but definitely forwardish, right? You guys see that? Okay, so I see that both of these guys are pulling in the forward direction. So they're trying to get this this donkey to go forward. They're both helping with that task. But this guy on the left is pulling a bit to the left. This guy on the right is pulling a bit to the right. And it looks like he's gonna partially, if not completely, cancel out the right left stuff. You guys see that? Okay, so the way we're gonna approach this, like here's our game plan. We're going to break each of these vectors into components that align with this coordinate system. Now, this coordinate system, you guys see this dash axes, that's completely artificial. Right? You could just make up any coordinate system you want. But once it's established, you can analyze everything in terms of that coordinate system. You can say like, how much to the left and how much forward? And this guy, how much to the right and how much forward? Right? And then you can say, okay, well, we can figure out what the net force is right and left, and then what the net force is forward, and they're definitely both going forward, right? Okay, you guys get that for the gameplay, right? You guys ready to tackle this thing? All right, so I'm going to switch ink color to, what have I got? Okay, I got the light blue color. I think that'll work, right? So let's break these tension vectors. These could be like ropes with tension on them, right? Into components. Okay, so 500 newtons. Here's left and forward, right? See those dashed components, right? And the 1,000 newtons is pulling right and forward. I wonder how much right. I wonder how much forward. We're about to find out. Okay. So you see the first step to be able to analyze this is have to break those into components. Okay. Let's tag some numbers to these components. So let's start with the 500 Newton guy. The 500 Newton guy pulling forward to the left. Well, how much left? Who knows the answer to this? How much left? How much?
400 newtons.
400 newtons. Bing. winner. How do you know it's 400 newtons?
The 3, 4, 5 Pythagorean.
It is a 3, 4, 5 right triangle. Yeah, yeah. So you spot that with a 36.9 degree angle there, right? All right, so yeah, so Jackson spotted, that's a 3, 4, 5 right triangle. More generally, if it was any angle, could you do 500 times cosine of 36.9 degrees? Is that what you would do? Okay, and hey, it's 400. Well, 399.8, we'll call it 400. Right, you guys get that? So it's 400 newtons leftish. Hey, how much forward is this guy pulling? 300, right? You guys see 300? Right? Yeah, scroll up, get 300. I think so too. And all you have to do is scroll up, scroll over where the cosine is. We're popping a sign. Hey, 300. That's 300 newtons pulling forward, right? Okay. How about the 1,000 Newton guy over here, the strong guy? How much exactly to the right is this guy pulling? 600. Let's see. You might be right. What's 1,000 times cosine of 53.1 degrees? It is 600. All right, 600 newtons to the right. Right. Did you guys see already at this point that the donkey's being pulled more to the right than to the left? Right. Because I wasn't actually sure just from my picture that would be kind of close, but I can definitely see now. Yeah. If you did the tip to tail vector connection, it would be overall a little bit to the right, definitely forward and a little bit to the right. Okay. But how much forward for the strong guy?
800.
800, right? Scroll up, scroll over where the cosine is, pop in a sign. That is 800, 799.7. We'll call it 800. 800 newtons forward, right? You guys get that? Good so far? All right. So now let's find out what's the net force. You guys know this means the sum of forces, and then in the x direction, let's say horizontal. Sum of forces horizontal, right? Would that be, well, they're pulling opposite direction. So should I say 600 minus 400, right? 600 newtons minus 400 newtons, and that's 200 newtons in the x direction. Isn't that true? Right. How about what's the sum of forces in the y direction? Would that be 800 plus 300? 800 newtons plus 300 newtons is 1,100 newtons forward. Okay. Right. Okay. Guys got that? Okay. So the net force lateral is not very much. It's only 200 newtons, but because they're both pulling forward, I can definitely add those components to get 1,100 newtons. So this donkey is being pulled really hard forward and a little bit to the right. Okay, you guys see really hard forward, a little bit to the right. Are we good? Okay, now, okay. You guys ready for the last step? Okay. Last step is we're going to put those components back together and get the net effect. So actually, I think I can fit it down the space here, so you can get it all on one page. All right, donkey. Give some components going on here. Go a cartoon image. Okay. I know the donkey's being pulled to the right with 200 newtons. That's 200 newtons. And I should have dashed that. This is really a component still, right? It's going to be components of the final answer. Okay. And forward with 1,100 units. This is 1,100 newtons. Okay. You guys see to the right 200 and forward 1,100. Okay. Everybody good? Okay. And then notice I can connect those tip to tail vector connection, right? Okay. So if you go from the tail of the first to the tip of the last, okay, so the donkey's being pulled really hard forward and a little bit to the right. So we got ourselves a really skinny right triangle. Right? You guys got really skinny right triangle? Right? All right, so who's got questions so far? You guys followed so far? I think, yeah, let's check.
That forces that would not change the exact 400 and add.
Okay, yeah. So in the x direction, maybe I should label these axes. That would have made this more clear. So this is like the x-axis. This is like the y-axis, right? Okay. See on the x-axis, this guy's pulling right, but this guy's pulling left. Right? That means that they're telling the donkey to go different directions. This guy says, "Let's go to the right." This guy says, "Let's go to the left." Right? So overall, the 600 is a little bit more, is bigger than the 400, but just a little bit bigger. So you have to take the difference, right? See, if it was like 600 and 600, it would be a wash, right? The donkey wouldn't be going anywhere, right? But because they're both pulling forward, you can add them together. They're both helping each other in the forward direction, right? So that's why you add the 800, 300, right? All right, yeah, so that was a great question. Right, okay, so everybody okay so far then? We're good? All right. So to close this off, the net force has two properties, a magnitude and a direction, because all vectors have a magnitude and a direction, right? Okay. How can you get the magnitude? Boom, Stu's got it, Pythagorean theorem. So, well, here, we can do the math right here. So F total is the square root of a squared plus b squared. So that's 200 squared plus 1100 squared. Take a square root, that's some number of newtons, right? Let's see what that is. What's the square root of 200 squared plus 1100 squared? 1118, which is not much bigger than just the 1100. Right? So 1118 newtons. Right. So that's the magnitude that the donkey feels, right? There's two individual ropes, but there's one net effect, right? The donkey can only like move in one direction with some net force. That's the net force. Okay. And final question is, what's the direction? Suppose I want to get this little skinny angle right here. Guys, is that little skinny angle the same thing as this little skinny angle? Yeah. Right. So theta equals, now just eyeballing it, I might say, I don't know, maybe like 10 or 20 degrees, something like that. You guys think? Okay. How do you get that angle? You do an inverse tan of opposite over adjacent, right? So inverse tan 200 over 1100, right? Sorry, it's kind of small. Well, here, I should do this. I should write this better. Okay, so that theta, burn another paper for this, is inverse tan of 200 on 1100. So newtons. Okay. Okay, that little skinny angle right there, right? Okay. All right, so we're getting how many degrees off axis? And just eyeballing it, I was saying it was about 10 or 20 degrees. Okay. That's just to check the answer. Like once you get an answer, if you get something like 80 degrees, like, oh, whoops, I must have gotten the other angle. I must have gotten that big old wedge angle. Oops. Okay. So let's see. What's inverse tan of 200 on 1100? 10.3 degrees. 10.3 degrees. Right. As long as your calculator's in degrees, right? Your math teacher might possibly want your calculator to be programmed in radians for maybe for good reasons in that class. So for this class, for a long time, we're just going to use degrees. Yes.
Why are we being called
Okay, so this donkey's being pulled forward and a little bit to the right. But then in physics, we want to quantify what a little bit is. Like what is a little bit to the right? Right. And I know that it's 10 degrees off axis, right? So I can quantify like exactly the direction that the donkey's being pulled, because I know it's like almost completely forward, but not quite. Okay, it's a little bit there. Yeah, this little skinny wedge angle right here is yeah, it's about 10.3 degrees, right? And then if you did the wrong opposite over adjacent, you may possibly accidentally solve for this angle, and you would have gotten well, whatever 90 degrees minus that is, was that like 79.7, right? Okay. So this would be 10.3 degrees right of forward. Okay. All right. You guys get on the donkey? Okay. All right. So while you guys are digesting that, let's do big picture game. So the donkey's being pulled in two different directions. To make any sense of it, you have to assign an axis system, like a coordinate system, right? And split the vectors into components, and then say, well, what's the net force right and left, and get like a partial cancellation, so it's subtracted, right? And what's the net force forward, and they're both pulling forward, so I can add those components, right? So now I know the net force right and left and the net force forward. And then the last step is to put those components back together into this long skinny triangle, right? And so I can get the magnitude by doing Pythagorean theorem, which came out to 1118 newtons. Okay. F total equals the square root of A squared plus B squared, which is 1118 newtons, okay? And the angle that it's at, I can do an inverse tan of opposite over adjacent with the legs, right? Now I have to figure out, well, what's opposite, which adjacent, which angle am I looking at? Maybe I'm interested in what's this little skinny angle, like what's right of forward. Okay, I was eyeballing this and it's probably 10 or 20 degrees, like, yeah, you're pretty well this. Okay. Okay, you guys good? All right. All right, so we've done some projectiles over the last week, and we've done some two-dimensional motion and done some vectors here and vector components. So I've touched all the bases in the notes, and of course, you guys see the quiz in front of you, and we've done enough where you can't figure out all those. I think the best use of time, okay, yeah, I got about 12 minutes here. I think the best use of time is, since you do have the solutions provided, right? These are uploaded to Classroom, you guys got them, is to go through some of these, but just show you how to read like the music of the solutions, right? Like what does this mean? Like, why did I do like this or that step? Okay, so I do have some problems pulled up that I can just start going through myself, but before I do that, are there any specific requests for specific problems that you guys want to see? Like, why is the solution written this way? Or like, how does this work out? Yeah, what you got?
34.
Number 34. All right. 234. All right, so 34. Yeah. This is a good one. All right. So this guy kicks this ball. What they tell you here? They told you this height of this building is 7 meters high. And there's a 1 meter high railing around the playground. Okay, all right, so 7 meters, right? Ball down here, this guy kicks at a 53-degree angle. Ooh, 53-degree angle. You guys know that's gonna set a very nice 3, 4, 5 right triangle, right? That's why they take that angle, right? And they told you this horizontal displacement, 24 meters. They also told you the amount of time it takes for the ball to reach. Ooh, interesting. They didn't do the landing point. They did some point like right here above the vertical base of the wall. Okay, so from here to here takes 2.2 seconds. Is whenever they tell you the amount of time that's passed, that's a very convenient variable to have because it applies both horizontally and vertically. That's the only variable that applies both horizontally and vertically for projectiles, right? It's the amount of time, right? Because everything else has to stay strictly within, it's either strictly horizontal or strictly vertical, but the time is either way. It takes the same amount of time to get from here to here, whether you analyze it vertically or horizontally. Okay. Find the speed that the ball is launched, so how fast is this guy kicking the ball. The vertical distance that the ball clears the wall because it clearly sails over the top, but by how much? Okay. And then the horizontal distance from the wall to where the point lands. So from the wall to like it lands, it looks like on a rooftop playground in here, like how far across. Okay. All right. So here I can tell you guys verbally what the game plan is going to be, and then we'll switch over to the solutions and look at like exactly how this is done. So there's some vertical information, and there's some horizontal information that's provided. In fact, it might be a good idea to like, make a checklist. This is just my framework. I like myself. There's horizontal information and vertical information. There's time, displacement, and horizontal component of velocity. And then vertically, there's also those, but there's also acceleration due to gravity, which means a changing speed, which is time, acceleration. Okay, do y for like a height change, v naught y, and v final in the y direction, right, something like that. Okay. Now, they told you from this point to this point, they told you exactly what the horizontal distance is. Is that horizontal displacement? They also told you the time, and they told you this angle. Okay, so the fact they told you the time, that's there. Okay, they told you the horizontal displacement, they labeled it d, so that's what x is, right? Okay, you know gravity is 10 meters per second squared, or well, they probably use 9.8 in this college book, right? But either way, pretty similar answer, right? Okay, so do you see how like this is already begging to be solved as v sub x, right? You can just do x equals vt and solve that way. Okay. And then over here, how could you get this stuff? Right. Well, I'm already thinking, since they told you the launch angle, you can get that. So here's this ball is being kicked, here's the kick point. Okay. So of course, it's gonna go into the projectile, blah, 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 there's the dash path, right? I care more about, like, at the moment it's being kicked, I'll call this V kick. Right, I know this is 53 degrees. And however fast it's going across, isn't this equal to x divided by t? Isn't that true? X equals vt, that's the only equation you use for horizontal motion for projectile. This is whatever x divided by t is, or d over t, I guess, right? Okay, so when you know this component, v sub x equals, well, d over t or x over t, you know that, right? Guys, before we even did linear motion, I did a bunch of trigonometry with you. Remember you had that whole trigonometry page? So if you know one of these components of a right triangle, and you know this angle, could you maybe apply a little cosine and immediately get the speed of the kick? Right? That's not the only way to approach this, that's one way. In fact, but you could apply a tangent, you could also get v naught y. That's what this is, v initial in the y direction. Could you apply like, here, I'll set up both of those for you. Okay? So you could do cosine of 53 degrees is equal to v sub x divided by v kick. Okay. V sub x you would have very quickly figured out just by dividing these two. And v kick you could solve for by just doing a little algebra switcheroo with this cosine function, right? Okay. And then the two legs have a tangent relationship with each other. So tangent of 53 degrees, I know that's equal to v naught y over vx. Okay. Again, vx you would have already solved at this point, and just very quickly that divided by that. They gave each of those numbers to you. Okay. And then you can cross multiply and you can get how fast it's going strictly upward. Okay, which would be this number right here. So you have check have that. And then look at that point, you would have three known variables, wouldn't you? 1, 2, 3. If you have those three, that means now you can break out these equations. Now you'd want to use a modified version. So instead of x, I would say like y for vertical displacement. Instead of a, I might say g for like free fall gravity. Right? You guys good so far? Okay. So far it explains the problem. I'm just trying to give you guys the like the forest for the trees roadmap of like how you could approach and solve this. Let's go over to the solutions. Where's I had them right here. Didn't I? Wait a minute. All right. So let's see how I solved. What number was that again? 34. All right, thank you. 34. All right. So see how I solved here. Oh, okay. Did this whole thing down in just this half this page. Right. Oh yeah, look, exactly what I told you guys to do. If you do since you have the displacement and you have the time, you can very quickly figure out v sub x. Oh, okay, you know what? Actually, I crunched in also the cosine theta bit here, right, and got the kick speed as being this many meters per second. Right. Yeah, so I kind of crunched in together two things at once. Right. You know, v sub x is v cosine theta, where v is like the kick speed, right? Right. So the little substitution there. Right. And since you know, so how about this? If you rearrange it, solve for v. Right. Let's see. I would say that'd be x divided by t, and then divide the cosine theta down, get this expression. Right. So this is the kick speed, knowing the distance d to the wall. They said d, I'm saying x. Right. You guys get that? Okay. You know the kick angle because they gave that to you, 53 degrees. They did also happen to tell you how much time it passed to get there. Okay. So that expression in terms of variables, and that should be the thing that you get comfortable doing in AP physics, is solving in terms of variables. Right. Like I know each of these things is true. Write it down, and then you can do some algebra and just switch variables around. Right. So get comfortable doing that. Okay. And then beyond that, you could use this to find relationships. For example, if the ball had to have gone further, x, then you would have to have kicked it faster, right? Or if it went the same distance but it got there in a faster time, then the only way for that to happen is well, there would be now an inverse relationship. Okay, right there. All right. Okay, so plug this in and you can get the kick speed. Okay, you guys see that? Okay. So that is the total kick speed. That is what on this page I labeled v kick. Right, so we know that. Okay. Part B says find the vertical distance that the ball clears the wall. So that's this distance right here, isn't it? Okay. Now here's the way I'm thinking about this: is you could apply those kinematic equations on that green poster over there, And you could solve for y. Now, y would be this distance from here to here, like from the ground to where the ball is clearing, right? Wouldn't it be this whole thing, right? And then, since the actual question is, what's this distance right here above the wall? Okay, should draw this for you guys. Okay, the ball is doing this. Here's this building. Okay, here's the ground, right? Getting kicked from the ground. The vertical displacement from here to, oops, let me zoom out a little bit. Okay. From here to here could represent y, couldn't it? Could that be y, right? And then from here to here, they were calling this the height of the building h. So the distance that it clears, wouldn't this just be exactly y minus h? You guys see that? You guys see that? Okay. I bet I did some version of that in the solutions. Okay, guess that. Okay. Let's check that out. Let's see how exactly did I solve part B. Okay. Oh, yep, look at that. We got the first kinematic equation right there. Y equals v naught yt minus 1/2 gt squared. Okay. Now, what would we know already? Like, we know the time because they told us that. We know g because that we'll see it's like 9.8 meters per second squared. But the v naught y, that's to say, like, what's the vertical component of being kicked? At this point, it's not exactly been solved, but it's really close because we know what v kick is and we know this angle 53 degrees. Guys, can you say this is equal to this times sine of 53 degrees? Right? V naught y is v kick times sine 53 degrees. Right? Let's see if I did that substitution here. Oh, it's right there. Here's your v kick times sine 53 degrees. So this bit is telling you v naught y. You see v naught y? Times t, so many seconds. Notice I attach units to all these numbers so you can see, seconds describes the time, so it's gotta be the time. Okay. Minus 1/2 gt squared. Okay, that's 1/2 gt squared right there. Okay, so I'm getting a y of 8.13 meters, but remember that represents this whole distance from the ground to this point up here, right? It's 8.13 meters. Okay. So, oh, look at that. Therefore, the difference in height that it clears, you have to subtract the height of the building. Exactly what you guys just told me to do. Right? You guys just said, take the y value and subtract the height of the building, right? And that'll give you this. Right, you guys get that? Right, and then what's part C here? The horizontal distance from the wall to the point on the roof where the ball lands. So they're asking for, here's the ball landing, like crash down here. They're asking for this displacement right here. Isn't that true? Okay. You guys okay so far there? Okay. All right. So yeah, I've covered all the principles of how to solve all these problems. You guys got all the solutions. Here's how to read some of the music of the stories. All right, you guys have a great weekend, and I'll see you Monday for a lab.